Okay, that means we're being recorded. And the first thing I'm going to do is these three multiple choice questions. And then I'm going to find some multiple choice questions somewhere else from the question paper that I've opened up. Okay, right, this is just a warm-up session. What's the molecular formula of a hydrocarbon containing 86.6 carbon and a molar mass of that? Now, here we go. I'm going to do this quickly. Obviously, it's going to be 84.6 of carbon. And how much hydrogen? That's 15, I'm doing this in my head, 15.4% of hydrogen. Next thing I've got to do is I'm going to convert these percentages into grams. 84.6 grams and 15.4 grams of hydrogen. I'm going to divide them both by the relative molecular masses, okay, to get the number of moles, and therefore I'm going to initially try and find the excuse me, the empirical formula. So there we go, we get 7.07, and this is obviously 15.4. Divide them both by the smallest, 15.4 divided by 7.07 is a 2.18. It's a bit of an ugly ratio, but it's roughly 1 to 2. Okay, so where do we have a 1 to 2? It's actually a 1 to 2.18. Okay. So I'm going to check which one of these are 1 to 2.18 by getting the big number, 44 divided by 20. That's 2.2. That's a ratio of 2.2 of the hydrogen to oxygen. The next one is 10 divided by 11. It's not going to be that. 22 divided by 10. This one is going to be 2.2 as well. And the last one is 11 divided by 5. It's 2.2. So it's one of these ones. Okay, but so it's one of these. And now with a molar mass of that. Why can't we just do it like that? So it's whichever one does that, which matches a molar mass of that. So it's 20 times 12. That's too big. 120 plus 22. 142, so it's C, isn't it? That was, I don't know why we even had to do all of this rubbish. We could have just looked at that and which one has the molar mass of 142. That's a bit boring. All right, which graph shows the relationship between the volume and pressure of fixed mass of an ideal gas? All right, ideal gas, high pressure, low volume. Okay, so this is low pressure, high volume. That's wrong. Low pressure, high volume. What am I talking about? Hold on, let me correct that. If the pressure is high, the volume is low, isn't it? So this one shows down here. If the pressure increases, the volume increases. That's rubbish. If the pressure increases, the volume increases. That's rubbish as well. One of these two, and it's not going to be like this, is it? These form these things, they eventually go to infinity and they never quite touch. So if the pressure is infinite, the volume is 0. All right, and I think these are called asymptotes. I can't remember. It doesn't look like the right spelling, but it's an asymptote thing. It's not a linear thing here, because that would mean there would be, at very high pressures, you get very small volumes like that. So it's one of these things. So the answer is A there. I don't think I explained that very well, but never mind. Percentage of that. All right. What's the percentage yield when 7 grams of ethene produces 6 grams of ethanol? Okay. So from 7 grams of ethene, okay, so the number of moles of ethene, which is ethene, it's 7 divided by 28, so that's the number of moles. So we'd expect the same number of moles of ethanol, but we want the percentage yield. So this is how much we expect of ethanol. So the expected amount of ethanol, that's the number of moles of ethanol. Okay, that's how much we expect. But if we produce 6 grams of ethanol, so let's get rid of this for now. That's the number of moles of ethanol times that. by the relative molecular mass of ethanol, which is 46. That gives us the mass of ethanol. All right, that's the theoretical yield, so that goes in the bottom. But we actually got 6 times 100, and that's the yields of ethanol. So which one is that? The 7 times 6 times 100. It looks like A, I think. Yeah, the 46 is definitely on the bottom, so that's wrong. What's this? The 28. No, 28's on the bottom as well. And there you go. So it's that one. Hope that makes sense. But there you go. So I'm going to, they were just for fun, those first 3. Now we're going to go to the organic ones. All right. And we've got quite a long way. They're right at the bottom. Okay. The organic ones are normally quite easy, really, normally. Okay. There's a rates one. God, right at the end, aren't they? Here we go. Here, gosh, that started ages. All right, let's have a look at this one. A nice, easy organic. There we go. Now I'm going to send you the PDF of this, so I want this nicely done. What monomer could create this polymer? Okay, so we have to find out that. This is the way we do these things. We, very simply, we pick any bond here and make it a double bond. There, I'm making that one a double bond. And get rid of everything on the left, everything on the right. And what's this? This is 1, 2, this is butene. Butene, so the answer is A. Simple as that. Next. This is a nice easy one as well. Okay, which one is a secondary alcohol? Secondary alcohol, the OH, must be connected to a C. Oh, that's a wrong color, isn't that? Must be connected to a C, connected to an H, and then 2 R groups. To be a secondary alcohol, this is a primary. Let me get a nice color here. This one is a primary. A is a primary. This is a secondary. This is a primary. And this is a tertiary. So the answer is B. Okay, so far so good. Any questions from our audience? Are we all good so far? Excellent, well done there. Right, let's have a look at the next one. These are straightforward, aren't they? Oh, this one's tricky. I might need help with this one. All right, I get these confused. All right, so we've got a compound there. It's a cis-trans isomer. It's not a cis-trans isomer. It's a geometrical isomer, I should say. All right, so let's figure out what this is, the name of this. Well, first of all, let's name the thing. Number of carbons in a row. There you go. It's 4, so it's bute, something or other. There's a double bond there, so it's butanene. Okay, so it's, these 2 at the bottom are rubbish. Okay, because we want it to be called butanene somehow. Now, let's have a look. We've got this. Is it the E isomer or the Z isomer? It's definitely 1 bromo, 1 chloro, butanene. But is it the E or the Z isomer? Now we use, what are they called? Some CIP rule or something. I should know, but I don't. What we do is we do it on molecular masses. Now we look at the left-hand side. We compare bromine to chlorine. Which one has the highest molecular mass? It's bromine. So this has priority 1. And then we look over the other side and we see which one. We compare hydrogen to carbon. And the carbon has priority 1 because it's a bigger molecular mass. So both priority 1s are on the same side. So that means EZ, and this is trans. This is how I remember it, cis. So it's the Z isomer because they're on the same side. Z is the same side. Okay, now that one's a bit tricky. Whoopsie daisy. Are we okay with that one? Oh, well done, Janet. Oh, I sorry, didn't realise you wanted to play. Yeah, I should have said, well done. You got that right. Sorry, dear. I should involve you a little bit more, shouldn't I, in these? Okay, yeah, I'll slow down a bit because you want to play as well, which I have no problem with. Okay, so let's paste this. Which one is chiral then? What do you reckon there? I'll give you 30 seconds. Go. Da, 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 da. Da, 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 da. Da, 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 da. Oh, you don't know. All right, no problem. Okay, now we could do it a few ways. We're looking for 4 bonds, aren't we? We're looking for 4 different groups. We're looking for 4 different groups around the carbon, and that's going to make it chiral. Now, the answer is A, by the way. It looks like it to me anyway. Now, why is it A? Well, this carbon here has an ethyl, it has a hydrogen, has a bromine. Oh, no, it's not A, because the 2 ethyls are the same. I'm wrong. So that's rubbish, isn't it? The reason it's not A is because the 2 ethyls are the same. So it's got to be 4 different groups. So if we look at the second one, well, there's an ethyl, there's a hydrogen, there's a bromine, and there's a methyl. So it's this. The answer must be B. Have a look at this one. This one is the closest we can get to being chiral. It has that funny group. It has a carbon, that's a hydrogen, got a methyl. But that group and that group and that group are the same. So it can't be that one. And this one, well, it's got 2 hydrogens on the same carbon, so it can't be that one either. Are we good with that? Janet, you good? Excellent. I know I'm going fast here, but life is too short, isn't it? Right, the next one. Let's see. I'd like to do as many as we can. If there's any problems, we can fix them, can't we? All right, what stages are needed to convert nitrobenzene into phenylamine? In 2 steps. Before we do anything, I should know this. So from nitrobenzene. So I'm not even looking at the answers. And you should know this in your organic chemistry, or you should be doing this. Do you know the answer, dear, before we go on? Okay, I'm starting off with nitrobenzene. Okay, and then I want to get from nitrobenzene, I want to get to phenylamine, this one. NH2. Janet, do you know that one? Yes, no? Finger up, finger down. Okay, right, this is a really common reaction. This is called a reduction. Okay, we're going to reduce that group to the NH2 group, and it's a reduction. Now, remember this, because it's a funny one. What we do is reduce it with tin and concentrated HCl. Okay, so I'm looking at all the options, and it must be that. Okay, now, if we get tin and concentrated HCl, we're going to end up with this. We're going to end up with the NH3 plus Cl minus, and we have to remove one of these protons to get phenylamine. And how do we remove a proton? We react it with sodium hydroxide, and it pinches that proton over there, and it gives us phenylamine. So the answer is D. Now, Janet, you got to know you're organic, eh? And the rest of you guys as well. I'm talking to all 5 of you, even though only one is here at the moment. All right. Next one. This one is a weird one, and I might need help here. Janet, can you help me with this one? Because it's a term that I'm not that familiar with, the IHD. Well, I think I know what the answer is by looking at it. But do you know what the answer is? Any luck there? Is it 1? No, it's not 1 actually. It's how many this collection of molecules, this collection of atoms, how many hydrogens we can squeeze onto it to make it fully saturated. So you're thinking of we're putting 1 there. Okay, and we can indeed. Okay, and therefore the answer would be B. But also, if you open up this thing to make it a straight chain something or other, you'd need 2 more hydrogens. So the answer is 1 for that bit, and opening up the ring is another 1. So the answer is actually C for 2. All right, look that one up. If you have a problem, ask me. Okay, well done, Janet. You're doing good. Whoopsie daisy. Next one. Oh, this looks awful, but we'll try and figure something out here. See if we can do this one. Okay. There we go. Whoopsie daisy. Put that there. Now that's 100. I'm going to send you this this PDF of this thing, so we don't have to take any notes. What's the ratio of the areas of the signal of proton NMR in pentan 3O? I'm going to draw pentan 3O. And I want you to try and guess the answer, Janet. Pentan 3O. 1, 2, 3, 4, 5 for pentan. There's an OH there. Okay. Before we even look at the question, how many peaks will we get on the proton NMR of this guy? How many peaks? How many peaks? How many proton environments are there? 6. You reckon there's 6? I don't think there is. This one, that's one proton environment. But because the molecule is symmetrical, they're exactly the same as these 3. So even though I've drawn 6 hydrogens or whatever, they're all the same proton. So that's 1 peak. I'm going to draw the peaks over there. 1. The next one is, let me draw a different color. The slightly darker green. That one, and that one, and that one. They're exactly the same. Okay, so this is going to give us 2 peaks. These are going to form 2 peaks. The next one, let me grab a different color. It's a pinky one. There's 3 peaks, so we're going to get 3 peaks there. And the very last one, let's do this nice grey color. There's going to be 4 peaks in total because there's 4 proton environments. So which one's obviously rubbish? This one's rubbish because this says it's going to be 1, 2, 3, 4, 5, 6 peaks. There's not going to be 6 peaks. The other ones are 4 and 4 and 4. But what's the ratio? Well, there's going to be 4 peaks. So the first one's going to have 6 protons in it. This one. The next one's going to have 4 protons in it. This one. The next one's going to have 1 for this one. And the next one's going to be 1 for that one. So it's 6, 4, 1, 1. The answer is A. Are we good there? Oh, well done, Jenny. You got it. Nice one. Well done. That's not an easy question at all. I don't think that's easy at all. All right. Now you're going to do a weird one. Okay. I'm going to let you read this. Okay. Let's zap it up to 100. You can read this while I open another multiple choice. Okay, so you read that, try and figure that one out, and I am going, you won't know what I'm doing in the background here, but I'm opening up another multiple choice because I thought we'd could do non-organic stuff as well, but that's fine. So let's pick this one, random. Oh, bum, I didn't mean to do that. Okay, I've got to close that now. All right, forget that. Close that one. Close that one. All right, open this one. And open this one. Put that over there. Oh, which one do I open? The paper, that's good. And open this one. Excellent. So I'm all good. Now I'm going to go right to the bottom to get the organic-y ones. That's not organic, but yeah, we'll start off with that one. That's a weird one. All right, and then I'll get back to the questions. Okay, and we'll go here. And A looks, it's not D. Well, that's good. A looks right. What would be the most effective method to distinguish between liquid propanol and propan-2-ol? Observation of color change when warm, dichromate. No, that's not good. It's not right, I'm afraid. A isn't right there. I'll tell you why. It's because propan-1-ol will oxidize to an aldehyde. Propan-2-ol will oxidize to a ketone. So the color change, believe it or not, with this will be the same. It will both go from orange to green. Okay, so you can't determine primary and secondary. If one was a tertiary, which one neither of these is, something like 2-methyl-propan-2-ol or something, then you would. But primary and secondary is both oxidized, so you get color change. So 1A, I'm afraid, is wrong. Determination of the M over Z values in mass spectrum. That's possible. We'll come back to that. Determination of percentage composition. No, they're isomers. NMR spectroscopy. Yeah, you could choose this. Definitely. Why not D, Janet, out of interest? I'm going to check. Why Why not D? Jenny's gone. Let's have a look at propan-10. 1, 2, 3. They don't, dear. They do not have the same proton environment. So let's have a look at propan-10. There's propan-10. You've got to draw these to realise proton environments. And let's have a look at propan-2. Now, propan-2, and I want you to tell me how many peaks we'll get in propan-10 and in propan-2. How many environments are there in propan-10? Do you think? How many peaks will we get? Propan-10, this one. No? If you don't want to do it, I'll do it. I don't mind. Up arrow, down arrow, up thumb, down thumb, sideways thumb. No? Oh, okay. Shall I do it? And we'll do it together. Shall we? All right, you're drawing. All right, let's do it together. So 1 proton environment, 2 proton environment, 3 proton environments, 4 proton environments. So we'll get 4 peaks here. Let's have a look at the other guy. Have a look at propan-2. How many peaks will I get here? This, and this, and this, and this are all the same. So that's 1 proton environment. You can't see. Why can't you see? Is it as your internet gone weird or something? Hello? Oh, nuts. You know what? That mine was going bad. Loads yesterday. It sucks. It really does. All right. Anyway, I don't know. Refresh, dear. Do what you got to do. All right. I'll continue as though even if you have to log out and come back in, I'll continue because you'll be able to see the video of this anyway. All right. So anyway, so we've got 1 peak there, 2 peaks there, 3 peaks there. So using NMR, you'll get 4 peaks for propan-10, but you'll get 3 peaks for propan-2. Okay. All right. There you go. Is it getting better or is it still bad? All right. Well done. So do you get the answer? You follow the answer? Are we good? Excellent. All right. Well done. Let's have a look at the next one now. Whoopsie daisy. All right. Now, this one is a killer. Well, it looks like a killer to me, I must admit. And we shall see how you are with this one. It's not really organic, but obviously we've got to know these ones, haven't we? All right. They're all bad. All of them are bad. Okay. So let's put this one up here. Now, oh gosh, look at this. What is the order in increasing pH of the following solutions of equal concentration? Oh my word, isn't that awful? Now, Janet, do you want to have a look at that and have a go? Or do you put a downward thumb if you think, oh, for God's sake, not this one? Actually, it's not too bad. It's not too bad. Can we look at the last question again? Yeah, sure. There we go. Are you okay with that? The different peaks. Yeah, you know what? There'll be different peaks. They'll be in different positions, but we don't even have to look at the positions. Propan-10, excuse me, propan-10 will have 4 peaks in proton NMR, and propan-2 will have 3 peaks in proton NMR. We don't even have to look where they exist. One's going to have 4 peaks, one's going to have 3 peaks. So we can distinguish between the two using proton NMR. Is that okay? Is that all right, Janet? All right. Now, look, let's have a look at the other ones. A is wrong because they both oxidize. C is wrong because they'll have the same percentage composition. You could determine the M over Z values of the molecular ion in the mass spectrum, but the M over Z value of the molecular ion in the mass spectrum will be the same. They'll be the same in both cases. Okay, because the molecular ion just gives you the molecular mass, and these are two isotopes of each other. Does that make sense? I hope that makes sense. This is chemistry's hard, eh? For sure. Now this one, what's increasing pH? Okay, increasing pH. So we want, so if the pH is increasing, pH increases that way. All right, if pH increases, acidity decreases. Isn't that interesting? So what I'm going to do, what's happened there? Something happens. Oh, Janet, did you? Oh, you went and came back. Okay. All right. What I'm going to do is this because I think it's worth looking at. Let's have a look at an acid here. Janet, are you okay? All right. Good stuff. All right. Let's have a look at I don't know. H3BO3. I've never heard of boric acid, I guess. Who knows? Now, when that dissociates, it's going to give us the H plus ion and H2BO3 minus ion. And therefore, Ka is going to equal the hydrogen ions times this ion divided by the concentration of the acid. Okay. Now, in other words, what I'm trying to say here, I wouldn't bother doing this in the exam, but Ka, the bigger the Ka, and we should all know this before we go into the exam, the bigger Ka, that means there's more products. Okay, and that means, and one of the products in this case is the hydrogen ion. So the bigger the Ka, the more acidic. So Ka, bigger Ka, it's more acidic. Now, annoyingly, because it's the total of the opposite, the bigger pKa, it's the less acidic. Isn't that annoying? That's just annoying, isn't it? So what you've got to do, you've got pKa here, and you've got Ka here. So what I would do is I'd change these two into pKa's, and I'm going to do that now. So we've got log of 5 exponential minus 2, and that's minus 1.3. Forget the minus, it's 1.3. And the other one is 5.8. Gosh, exponential minus 10. That's a tiny one, isn't it? Log of 5.8 exponential minus 10. And that's 9. This is very weak. 9.24. So I've changed them all into pKa's. And now the smaller the pKa, the most acidic. So which one is the smallest? This one. So that's the most acidic. So this one has to be on this side. So which one is that? It's A, isn't it? Simple as that. Are you okay with that? That was a bit of a long way around it. Yeah? Are you all right with that? Yeah, it's not a hard one in the end, was it? All right, there you go. So there we are. That was that one. Now let's have a look at another one. Forget that. Let's have a look at the organics. Oh gosh, this one, nice one here. All right, paste there. Make it 100, and there we go. All right, let's have a look at this. Okay, that's still working, which is good. All right, which will react with a halogen by electrophilic substitution mechanism? Oh, that's not a hard one if you know your stuff. Do you know what the answer is there, dear? Which one will react by electrophilic substitution? A, B, C, or D? Well done, it's A. Benzene is always electrophilic. Benzene is always electrophilic substitution. Okay, so this is electrophilic substitution. This, how it will go on that. Do you know what C mechanism will be? How a halogen will react with C? It's a good guess if you understand this one.